To branch or not to branch, this is the decision before us. So far, the programs we have written have been very short and simply flowed from top to bottom. In this video, we will learn more about flowcharts and how they can help us visualize the operations of our programs. We will learn how the values of the flags can help our programs decide what to do next. And we will learn how subroutines can reduce the size of our programs, reduce the opportunity for errors as we write our code, and save time in code writing. Earlier, you were asked to fill in this square to help someone understand the process of counting from 1 to 10. If I asked you to count from 1 to 10, without thinking, you would immediately begin 1, 2, 3, 4, etc., intuitively stopping when you get to the number 10. For the computer, there is no way to permanently teach it how to do what you learned many years ago. Instead, we write programs, which are nothing more than a set of intentional instructions meant to instruct the computer on how to process data to achieve the end result we desire. When looking at the bigger picture, you might write something like add 1 to A, then shout out the answer in the middle box. You have now created a visual image of the process of counting from 1 to 10, but there would be a few minor problems in your simple 3-box description. Can you see the 3 gotchas with the simple instructions above? Let us manually step into each square in the flowchart, keeping track of each of the processes, just like we have asked Visual Studio to do so many times already. First, we set the variable A to 1. Secondly, we add 1 to A and store the result back into A. A plus 1 is 2. So we store the value of 2 in A. Third, we shout out the current value of A, which is 2. Fourth, we ask the question, is A greater than 10? Since A is 2, it's not greater than 10, and we return to step 2 and repeat. A plus 1 is now 3, so we store that in A and shout out 3. Repeating the question, is A greater than 10? And it is still not, so we return to step 2 again. This continues until we pick back up with A currently being set to 10. The question is asked, is A greater than 10? Since A is equal to 10, the answer to this question is still no. So returning to step 2, we add 1 to the current value of A and shout out 11. This time the question is answered with a yes, and the program stops. Have you realized the 3 problems with the simple flowchart above? First, we don't shout out the answer until it has already been incremented to 2. So the shout out instruction is after the add instruction. Second, the challenge question, is A greater than 10, is after we've already looped back and added 1 to A, giving it the opportunity to reach 11. Finally, the third box asks the challenge question, but there is no clear direction on what to do with the answer to that question. We assumed that you should follow the arrow to the right, but how are you sure? And were you supposed to follow the arrow if the answer was yes, or if the answer was no? This short exercise demonstrates the importance of using flowcharts to show how a program will operate, but to make them more useful, we are going to add a few more flowchart symbols to help clarify the different components that make up a program. The first shape, and we're already familiar with it, is the rectangle. We used it for all functions up to this point, but is primarily used for calculations or assignments within our programs. To mark the start or end of our programs, we will use a rectangle with rounded corners. The decision is depicted with a diamond, since it has 3 points for the decisions yes, no, true, false, less than, equal, or greater than, etc. Input is a rhomboid or a rectangle with slanted sides. This could be a keyboard or some other type of sensor. Output is a rectangle with the bottom torn, kind of like a piece of paper torn from a printer. This could be a screen, printer, or other output device. And finally, a rectangle within a rectangle is used to identify a call to a predefined process. We will learn a little more about each of these symbols through our 4 sample programs that will make up the remainder of this video. Now, we will rewrite the earlier program to count from 1 to 10 using the symbols above and incorporating the gotchas we revealed. To begin with, every program has a start and an end. The first thing we need to establish is the preset value of A. Since this is built into the program, it uses a calculation or assignment box, not the input box. Secondly, we add a display box to shout out the current value of A. For our programs, we are using the register display in Visual Studio as our output or display. This is why we set breakpoints within our programs. Now that we have displayed the value of A, we will increment the value of A, storing the result back into A. In order to be less confusing, since A is rarely equal to A plus 1, we say A takes on the value of A plus 1 in order to distinguish this from some sort of unrealistic math truth claim meant to make us lose sleep at night. And finally, we have the challenge question to determine whether we will repeat the process again on our quest to count from 1 to 10. There are 2 possible answers to this question: yes, and we loop back up, or no, and we fall through to the next step. Flowcharts help us visually design and test our thought process before we write a single instruction in Visual Studio. Think of it as an opportunity for a sanity check. So, let's look at the decision box. How do we instruct the x86 microprocessor to make either a quantitative or a qualitative decision, such as, is A greater than or less than 11? This is where flags introduced in the previous lab come into play. Upon investigation of the x86 instruction set, you will find an instruction with the mnemonic CMP, standing for compare. The compare instruction subtracts the source from the destination and sets the flags accordingly, but does not change the value in the destination location. So if AX, or A in our program, is 9, for example, subtracting 11, the source, from 9, the destination, results in setting the carry flag. Remember, the carry flag is set when we overflow or underflow the register by adding or subtracting values that cause the register to cycle around. The carry flag is the way the microprocessor informs us that a problem may exist. For example, if the AX register contains FFFF hex and we add 1, the result is 0 hex, with the carry flag set to carried 1. If we simply count on the value of the AX register, we would think that 65,535 plus 1 is 0. So back to our compare instruction. We now know that using compare will give us a carry flag value of 1 if the source value is greater than the destination value. Now we need to find an instruction that will jump us to a specific location in the program when and only when the carry flag is set to 1. It turns out that the JB instruction, jump below, will do this. Interestingly, this jump instruction has two other names that could also be used, and there is no preference other than making the program easier to read. You could also use the JC instruction, jump if carry, or the JNAE, jump if not above or equal, and the result would be the same. But since the flowchart question is A less than 11, the yes, it's below answer seemed the easiest to translate to the x86 instruction. The x86 microprocessor has over 30 jump instructions, which allow it to act on the values currently stored in the registers using the values set or not set in the flags. If you remember from previous sections, almost all operations performed on a register, whether it's a math instruction, add, subtract, multiply, divide, etc., or a Boolean algebra instruction, and, or, not, XOR, or test, all of these instructions affect the flags. It is important to understand that data load instructions, such as move, do not modify the flags. All of the jump instructions are considered to be conditional, meaning that they are only executed if a certain condition is met, except one. There is only one unconditional jump instruction, the JMP instruction. The JMP instruction directs the program to the given label regardless of anything that happened prior to the jump instruction, or with no regard to the contents of any flag. In contrast, the 32 other conditional jump instructions that jump completely based on flags, and in particular the carry flag, the parity flag, the zero flag, the sign flag, and the overflow flag. It can also be seen that many of the jump instructions are synonymous, leaving only 17 unique jump instructions. Now we can take advantage of these jump instructions to modify the flow of our programs. There is one more process that will help us become more efficient as we write more complex programs. In computer terminology, sets of instructions are referred to as code or programs. To think in broader terms, they are routines. Just like in our first lab, we discussed the process or routine of mowing a lawn. Likewise, we have been teaching the microprocessor routines such as adding two numbers or counting. Let's say we want to multiply by 2, add 1, and divide by 2. We could write something like this. But what if there was a way to tell the computer to repeat these instructions more than once? First, we could pull out one section of the repetitive code, add a name or label with the mnemonic proc, P-R-O-C, for procedure, and then an end procedure mnemonic at the end, ENDP. Now, whenever we wish to use this code in our program, we simply write call followed by the procedure label. Now that we are familiar with the ability to use the flags to teach our x86 microprocessor to make decisions based on calculations it is performing, and we have the ability to reuse code multiple times by placing it into a subroutine, let's look at a few example programs. Before we get to the example programs, since you're going to need Visual Studio, let's start Visual Studio and load our template. Once you have the template loaded, we're going to make two changes to the Visual Studio configuration. First, we are going to turn on the flag display so you can see the flag values as your programs are running. To do this, simply set a breakpoint in your program, even though it's just the template, and press F5 to run the program to the breakpoint. Once your program is running, to display the flags, simply right-click on the register display and check Flags. Click the stop icon to stop the debugging session. Also, while you're here, do you have a pesky black command window that you have to keep closing? If you do, follow the instructions in the window or click Tools, Options, scroll to Debugging, and then near the bottom of the general list, you will see Automatically close the console when debugging stops. Make sure this is checked and click OK. For each of the examples below, you will find a complete code at the end of the lab manual section for this video. It is recommended that you watch the video section related to each program, then pause the video, enter the program as listed in the lab manual. Make sure the program runs and gives the correct and/or expected answers. Then complete the analysis questions listed after each program's flowchart, some of which may ask you to make modifications to the programs before rerunning them. For our first example program, we are going to revisit the counting program from the beginning of this video. You are the lead embedded microprocessor developer for the Acme Widget Company. Your project manager approaches you with a project to count the number of widgets being produced on the assembly line. The packing boxes the widgets are being placed in only hold 10 widgets, so you decide to write a program to count to 10. The first step is to convert each of the boxes or steps in the flowchart into their corresponding x86 microprocessor instructions. Sometimes one flowchart box will result in more than one assembly language instruction. This is dependent on the type of box, such as the decision box generated 2 instructions, or the detail you have used to define the box. Pause the video, enter the full program from the lab manual, set your breakpoint or breakpoints as suggested or as you see fit, run the program, observe the results, and answer the analysis questions for this program. I'll see you after you've answered the questions. Welcome back. Your project manager was really excited with the project you just created. After discussing the project with the assembly line supervisor, they realized that if 2 boxes could be filled simultaneously, they could actually fill more orders every day. Your manager asks you if you are up to the challenge of dividing the widgets among 2 packing boxes. In order to accomplish this, you've decided that since you just got done programming the microprocessor to count to 10, you'd simply build on that code and have it tell you which of the numbers between 1 and 20 are odd or even. So you start your flowchart. You are going to count to 20 since you're filling 2 boxes with 10 widgets each. In this program, you've decided that you're going to store the actual number from 1 to 20 in the lower part of the A register, and you're going to set the upper half of the register to 00 hex if the number is even, and FF hex if the number is odd. So the sorter can just check for either 00 or FF to decide which box to put the widget into. A fellow programmer suggested that you use the shift right instruction since it divides by 2. They tell you to think about how this could help you with your program. You agree with the other programmer, remembering that when you divide an even number by 2, the remainder is 0, but dividing an odd number has a remainder of 1. Now you start seeing where the flags can be used to make the microprocessor change how it flows through your programs. Once you've determined whether the number is odd or even, you use that information to set the high order part of the AX register, then use a breakpoint to check the value of the AX register to make sure it's what you expect to see. Finally, you use the same steps from the previous project to increment the counter, check to see if we've made it up to 20 before stopping. Pause the video, enter the program, run it with some breakpoints set to make sure that it functions as expected, answer the analysis questions, then we'll see you back here for our next project. Your project manager spoke with the president of Acme Widgets, and based on your success with these 2 projects, they have decided to implement a new incentive program and have selected you to write the program to make it work. You excitedly ask for an explanation. We are going to count the number of widgets the workers build in each of 3 assembly lines, and the one with the highest number of widgets at the end of their shift is going to win a gift card. Can you write the program for the microprocessor that will tell us the largest number of widgets produced out of the top 3 assembly lines? You start your process by thinking, I can look at the number of widgets for the first 2 lines. If the first is larger, I can compare it to the third. If the second is larger, I can compare it to the third. This sounds like a solid plan, so you set off to design your flowchart for this project. Here are your thoughts. You will put the number of widgets the first 2 assembly lines produce into AX and BX. Then check to see if the value in AX is greater than the value in BX. If it is, follow the right branch, and you'll put the number of widgets for the 3rd assembly line into CX, then compare CX to AX. If AX is greater than CX, you follow the right branch and set AX equal to AX. If AX is less than or equal to CX, then you will follow the left branch and set AX equal to CX. Back to the first branch. If AX was not greater than BX, you follow the left branch and set CX equal to the number of widgets for the 3rd assembly line, then compare CX to BX. If CX is greater than BX, you set AX equal to CX following the right branch. If CX is less than BX, then you set AX equal to BX following the left branch. Finally, you display, using a breakpoint in your program, the value of AX, which contains the largest number of widgets produced by the 3 assembly lines. You sit back looking at this flowchart and think to yourself, wow, this might be the most complicated flowchart I've ever created. Pause the video for a moment and try running through the flowchart manually using the numbers in the lower left corner. And then, if you're ambitious, switch the order of the numbers for N1, N2, and N3, or try different numbers. Once you're comfortable with the flowchart, use the program listed in the lab manual to see this program in action. Remember to set some breakpoints, especially at the no-op, representing the display box for the AX at the end. Answer the analysis questions for this program, then restart the video to see the final example program. Okay, pause the video now. See you soon. The incentive program to reward the highest producing assembly line was a success. In fact, your project manager says it was such a success, they want to roll it out for all 6 assembly lines. You envision what it might look like for just 4 assembly lines, and then you remember learning about subroutines. So you think, what if I only have to worry about 2 registers, AX and BX? I check to see if AX is greater than BX. If it is, I leave the larger of the 2 values in AX. If BX is greater than AX, I move BX into AX. With this simple evaluation, AX always contains the larger of the 2 values. Now you realize the program to check 6 assembly lines is much less complicated. In a few moments, I'll ask you to pause the video, review the flowchart. Take time to understand the benefit of using a subroutine to repeat code over and over again. After you've studied the flowchart, including the subroutine calls, load the program into Visual Studio and see how it executes. Maybe add a breakpoint at each subroutine call instruction to see what is in the AX and BX registers just before each call to the subroutine. This is the end of the video, but before you stop watching, you've learned a whole lot of stuff this week. Do not hesitate to repeat the video or reread the lab manual. This week may have made you get a bit of a headache. It's not really complicated. There is just a whole lot of information trying to teach the microprocessor how to think about things you don't even think about. Don't feel frustrated if you don't understand something. Reach out to your colleagues, your fellow students. They're in the same boat. Friends and study partners make this stuff easier to understand. Here's a real cool tip. Experiment with Visual Studio. You can't really break it. There are no parts to blow up. If it doesn't work, figure out why, fix it, and learn. Try changing instructions, especially the jump instructions. See if you can make these example programs work by changing instructions, especially if you can make them better. The important thing in programming, as cliche as it is to think outside the box. There are many tried and true ways to optimize, such as the XOR instruction being used to set the registers to 0, but the rest of the microprocessor programming world is in front of you. All microprocessors, programmable interface controllers, programmable logic controllers, and field programmable gate arrays all work the same way. This is the process to control and master all of these devices. If you learn nothing else from this week's lab, pay attention to the flowchart process. This can be used in all areas of your life. It's really about critical thinking. See you next week.